negative. If we're out here on the positive side of the number line and we're getting less positive and we want to become negative, what number do we have to go through? 0. We have to go through equilibrium and we have to go through 0. So there will be a point as we raise the temperature on this equation where we go through 0. Okay? So what if we have 0 equals delta H minus T delta S? And what we do is we assume that these standard numbers don't change very much. That's our assumption. Okay, that's our assumption. They don't change very much. But now what do we have? We have T delta S is equal to delta H. Our temperature is equal to delta H divided by delta S. Alrighty. So when the standard is equal to 0, our delta H, this just does what I did, and that would be our answer. Finally, when we got to 835.1 Kelvin, our reaction would just change from being non-spontaneous to being spontaneous. All right. Now, you can imagine that if you have thermodynamics, and if you're talking about whether something is spontaneous or non-spontaneous, then you're going to want to be able to relate that to your equilibrium constant. So this is a pertinent fact. Our change in our standard free energy for a reaction is the change in free energy when pure reactants convert completely to pure products. Another fact that we know is that a product-favored systems have equilibrium constants greater than 1. Therefore, both our change in our standard free energy of reaction and our equilibrium constant are related to reaction favorability. And our equilibrium constant is related to reaction favorability, and so too our change in Gibbs free energy for a reaction. The larger the value of K, the more negative the value of the standard change in free energy for a reaction. Now, this is our relationship between the free energy and the ln of the equilibrium constant. I don't really have a good derivation of that. It involves things like calculus and summing and stuff like that, which I'm sure you don't want to do. Now, remember, this is R, which is just our old friend, the gas law constant. But if you use the gas law constant, 0.0821 atmosphere liters per mole Kelvin, you'll get the wrong answer. What do we measure our change in free energy in? We measure it in joules or kilojoules, right? So our R is equal to 8.31 joules per Kelvin mole. If you, somebody asked me about that, the better way, when you're typing up a PowerPoint, it's very hard to make equations like this, but that's what that unit looks like. The joules are being divided by both the Kelvin and the moles. Now, again, remember that you may have calculated this in kilojoules, and this is in joules. So again, you have to watch out for your units, okay? So if you're off by a factor of 1,000, check into your units, okay? That might be a place where you're off the track. All right. That means that if we have if we have delta G information, we can use that delta G information. This could either be calculated using delta H's and delta S's for a reaction, or it could be calculated from standard free energies. Whatever, this is what the change in free energy is for this chemical reaction. We remember that we're going to use a gas law constant that has the units of joules, so we convert this to joules. And we have to take our ln of K is equal to 1.94. Now, this is just like when we had to, if you have a pH and you want to have the concentration of the hydrogen ion, the base for an LOG is 10. Here the base for a natural log is E. So in this particular case, what did we do? We took E to the negative 1.94. Okay, so the way you go from ln of K to K is you take E to whatever your answer is, to whatever ln of K is set to. Now you'll notice we had a slightly positive value, and so here we have a K, which would tell us that it's not product favored, it's reactant favored. Why? Because it's less than 1, right? Alrighty. So when our standard free energy is greater than 0, then K is less than 1.
So would it be the opposite if our value was less than 1 and K would be greater than 1?
Well, yes, sorry. So, and that should make sense, right? Because if we raise a base to a positive, we'd get a positive here, and so we'd get a greater than 1 value, okay? All right, just one thing, and then this might be where we start tomorrow. Delta G is change in free energy at non-standard conditions. So remember, we have a very specific place where we are when we're talking about standard conditions. However, we can make a relationship between our free energy change at non-standard conditions, and I'll write it down on the board. Our delta G, and this delta G is at non-standard conditions. And that is equal to our delta G at some standard state plus RT ln of Q, where Q is not the equilibrium constant, but it is the what? Reaction quotient. If we're talking about a non-standard delta G, we're talking about a situation where we are not at equilibrium. When Q is equal to K, of course, the reaction is at equilibrium. When delta G is equal to 0, the reaction is at equilibrium. Alrighty? That's about it. We might as well go home. Thank you very much for your patience and attentiveness. I will post homework, like I might even post it before I go home. So I know that you guys are probably getting sick to death of chemistry.